Hi everybody, I hope this video finds you well. Today we're going to be finishing up section 2.5 as a sort of follow-up to the computational video that was posted up just a couple days ago. I do want to just briefly, before we get into some of the discussion of this more theoretical side, we'll be proving a couple little theorems here and sort of building our way to understanding the solution set overall of a system of linear equations. I do want to just briefly go back over the sort of pieces we saw from the previous one. So if we just quickly scroll back, this is the sort of the document that we looked at in the last video. Keep in mind that we solved this system here, which was a system with 4 equations and 3 unknowns. And we did all this work and we ended up getting one unique solution. And we sort of commented that this was connected to the idea that the rank of the matrix and the rank of the augmented matrix were the same, and those values matched the number of variables. Then in this example, we worked on a system of 3 equations and 4 unknowns. We found that this system was inconsistent, meaning that there were no solutions. And we saw that that was sort of connected to the idea that the rank of the original matrix was different than the rank of the augmented matrix. Finally, we did this example here, which was a system of 3 equations and 3 unknowns. We also made note that it was a homogeneous system of equations. So we were confident from the very start that there was going to be a solution, because we could just imagine using 0 as a value for every variable. But we worked through this and we found that not only was 0 a solution, there was actually an infinite set of solutions, right? And we saw that that infinite set of solutions had this form here, which made use of a free variable, or what is often called a free parameter. And we noted here that just like the first sort of example, the rank of the matrix and the rank of the augmented matrix were the same. But in this case, that was smaller than the number of variables. And we also noted that the difference between these ranks and that number of variables, 2 versus 3, is exactly the number of sort of parameters that we needed to use. So in this video, what we're going to do is basically sort of show all of that in general. So we're going to be sort of working our way through proving what are sort of referenced as little lemmas. Lemmas are just sort of pieces of a proof that sort of can make up a more general theorem. We could state each of these as their own theorem, but it's more sort of standard mathematical practice to prove all these individual results, put them all together into one main theorem sort of at the end. The funny thing, though, will be that when we get to that main theorem in just a couple pages or a couple minutes of this video, we won't really need to prove anything for that main theorem, because the proof of that theorem will be in the proof of each of these little lemmas. So we'll get started. Some of these we'll give a pretty detailed proof of, some we'll give a sort of quicker proof, right? But we'll start off with lemma number 1. Now, lemma number 1 says that if you have a system, so you have system AX equals B, then the rank of the augmented matrix. So remember, the augmented matrix, remember, is taking the original sort of coefficient matrix and then adjoining that extra column of constants. Well, the rank of the augmented matrix has only 2 options. It is either equal to the rank of A, so it is the same as the original rank, or it is the original rank plus 1. I don't think a big sort of proof of this is sort of necessary. This should be pretty clear. First of all, what this is basically saying is that when you create this augmented matrix, you are adding 1 extra column. That extra column, once you put things into row echelon form, might yield a extra non-zero row. That's why we have that option that it could be the rank of A plus 1, or it might not yield anything extra, in which case you just have the original rank. Certainly, adding an extra column shouldn't decrease the rank, so that's why we don't have any options that say like the rank of A minus something. And since we only added 1 extra column, it doesn't make any sense that we would add 2 or 3 to the rank. So the only 2 options that make sense is that the rank remains the same or the rank goes up by 1. Now, as a little follow-up, your textbook doesn't actually show this result. They just make this comment, which is a natural follow-up to what we've just stated here, but ours is a little bit more precise. So as just sort of a note here, you should keep in mind that this means that the rank of a matrix is always less than or equal to its augmented form. That's another way of sort of saying exactly what this is saying, right? Know that the rank of the original matrix is always less than or equal to the rank of its augmented form. All right, so that is something we will reference, this sort of little fact here or this guy here, in some of these following sort of lemmas. So lemma 2 is going to actually talk about that sort of first case that we did in the previous video. So we're going to say we have a system AX equals B with A m by n. So that matrix is got m rows, n columns. So if rank of A equals rank of A augmented equals n, then this system will have one unique solution. So this is exactly the case that we saw in the first example in the previous video. It said if the rank of the original matrix is identical to the rank of the augmented matrix, and both of those things are equal to the number of variables or the number of columns of our original matrix, then we are guaranteed to have a single unique solution. So let's think about the sort of justification or proof of this. What I want to sort of do here is, let's suppose we put A into row echelon form. So we're not going to worry about the sort of augmented matrix. We're going to just think about the original matrix and imagine putting that into row echelon form. So what is that going to sort of look like? Well, if we do that, we should get this sort of matrix. Now, we don't want to write out too much, so we know it would have a leading 1, and then it could have a bunch of sort of garbage over here. Those could be just different values, whatever. Then we know it would have like a 0, another leading 1, bunch of garbage again, then like 0, 0, 1, bunch of garbage again, okay? And that would continue on, right? So that everything down here would continue to be zeros. And then here, this would be a 0, this would be a 0, and this would continue on until we have another sort of leading 1 there in that last column position. Now, just to touch things up a little bit, technically, if m was very large in comparison to n, then there could be a bunch of sort of 0 rows down here. So I'm just going to sort of put a little, I don't want to use a dash line here. Let's just say that this down here could be a bunch of 0 rows. Okay. So that is possible. Those 0 rows could exist if m is greater than n. Okay, but one thing that I do want to call your attention to, these 0 rows aren't going to matter anyway. The main thing I want to call your attention to is so that this 1, there has to be a leading 1 in every column. How do we know that? Well, we know that the rank is equivalent to n, which is the number of columns. So there must be a leading 1 in every column. So I am safe in making this assumption. These zeros here, of course, are just because that's part of the definition of row echelon form. This stuff up here is constants that we don't know and won't matter. And of course, there is the possibility that there's these additional 0 rows down there. So all just zeros. Okay, now let's imagine going ahead and putting on the augmented form. So if we augment this, right, we'd add our sort of vertical line, and we need to add in values. Now, all of these things would be different values, okay? And then what happens down here? Well, our claim is that from here onwards, these need to be all zeros. Why can I make that claim? Well, suppose that this first value here wasn't a 0. Say it was another leading 1 or a value that could be changed into a 1. If that was the case, then the augmented matrix, all of this stuff, would have all of the original leading 1s and an additional 1, meaning that the rank of the augmented matrix would be n plus 1 and not n. But we know by assumption that those ranks are equivalent, so this must be a 0. So as just sort of a comment here, right, this guy must be 0 since rank of A augmented equals rank of A. And then, of course, if that guy's 0, everything below that has to be 0 as well. So that's what our augmented matrix would sort of look like. All right, so what does this tell us then? Well, imagine we actually needed to solve this. What we could do is we could use back substitution. This would tell us, this row right here, would tell us whatever x sub n would need to be, because we have a leading 1, and then we have some value over here. Then once we know that, we could use that to go and use back substitution to find the next variable. So we could then solve this using back substitution. But notice that we're going to get a unique solution for every value, because this equation here will tell us about xn. Then once we know about xn, we can use the next equation to know xn minus 1, so on and so forth. Once we know all the values, we can use all those values to solve for x sub 1. That's what back substitution is. So if we solve this using back substitution, there will be a unique solution. And that's all we wanted to show, is that it will have one unique solution. So this can be a little bit weird because this is more of a justification rather than a formal proof, because I want you guys to sort of see the visualization. But just understand that the main idea here is that if the rank of A is the same as the augmented, is the same as the number of columns, then that forces there to be a leading 1 in every column. The 0 rows down here must correspond to zeros when we augment, because otherwise the augmented matrix would have a higher rank. And therefore, we have this set of leading 1s with a bunch of values here. We can use back substitution to get that unique solution. So we know that if the rank of A is the same as the rank of A augmented, is the same as the number of variables or the number of columns, then the system will have a unique solution. All right, let's look at some of the other cases. So we're going to introduce a lemma that talks about the second sort of computational example we did in the previous video. So let's just make sure we sort of keep our sort of same form here. So we have a system AX equals B with A m by n. Okay. We're going to say if the rank of A turns out to be smaller than the rank of A augmented, then the system is inconsistent. So in this lemma, we are going to show that if the rank of A comes in smaller than the rank of A augmented, then the system is inconsistent. Keep in mind, we don't need to talk about a case where the rank of A is greater than the rank of A augmented, because that very first lemma assured us that that's not possible. We know that the rank of A is either equivalent to the augmented matrix or is smaller than the rank of the augmented matrix. And now we're going to show that if it is indeed smaller, then the system is inconsistent. So, as our proof here, we're going to do this as a very sort of similar proof. Let's imagine putting A into row echelon form. Okay, now this time we'll sort of go ahead and talk about the same thing. So there's our sort of big A matrix, right? This time we don't know that it necessarily starts with a leading 1. Maybe it has some columns at the beginning that are 0. It doesn't really matter. So we're just going to assume that we can sort of start with a sort of leading 1 there. Then maybe there's some garbage stuff over there. Then we know a 0, a 1, and then some more garbage stuff. Okay, so on and so forth until somewhere down here we have 0, 0, a bunch of zeros, and then somewhere a leading 1. Now, again, we don't really care what's over here, so maybe there's some other stuff. Doesn't, again, because we don't know that the rank of A is the same as the number of columns, this guy doesn't have to be in the last column, so there could be other stuff over here. It doesn't matter. And then, of course, there are sort of 0 rows down here. And there's the potential that there are those 0 rows. Okay. Now, let's go ahead and think about whether or not we know if those 0 rows have to sort of be there. So let's think about the augmented matrix. So now we're going to augment this, right? And we're going to put in that there will be a bunch of values here. And this is the first step that sort of tells us that there must be some 0 rows here. The reason we know that is that the augmented matrix is supposed to have a larger rank. That means that the augmented matrix has an extra non-zero row that the original matrix doesn't have. Well, if that's the case, then there must be 0 rows in the original matrix so that the augmented matrix can sort of take one of those 0 rows and make it non-zero after augmentation. So what that means is that there will be some value here in that sort of first 0 row, and then maybe some other garbage down there. All right. So what does this tell us? Well, this is the picture that sort of corresponds to if the rank of A has to be less than the rank of A augmented. We can see here that this extra value here, matching up with those 0 rows do not contribute to the rank of A, but those 0 rows with that extra value there do contribute to the rank of A augmented. But let's think about solving this. So let's solve this system. But let's consider this equation here. So let's pull this guy out. We know that it's a 0 row in the original matrix, so that would correspond to the equation 0x1, 0x2, 0xn. But then it equals some value over here. And that value, right, this guy has to be non-zero. How do we know that it's non-zero? Because it needs to be non-zero to make that rank of the A augmented be larger than the rank of A. So we now have an equation that says 0 times every variable must be some non-zero value. That, of course, is impossible. So there are no solutions, which is exactly what we wanted to show. So what's the sort of summary of this lemma? Well, this lemma basically is saying that for the rank of A to be smaller than the rank of A augmented, that means first that matrix A must have some 0 rows. It also means that when we augment, those 0 rows have to correspond to some non-zero values to make the rank of A augmented larger. But that means that those 0 rows that correspond to a non-zero value in the augmented section give us equations that are unsolvable because they are 0 times every variable equaling a non-zero value. That's impossible, so there aren't any solutions, which means that the system is inconsistent. All right, now we're ready to turn to that last sort of situation that we looked at. So we've got one more sort of lemma to talk about here. So for this lemma, let's go ahead and set this up again. So we have a system AX equals B with A m by n. And we're going to say if rank of A equals rank of A augmented, but those are both less than n. Remember, we did the case where if rank of A equals rank of A augmented equals n, that was our sort of lemma number 2. That was the first situation we sort of analyzed. If rank of A equals rank of A augmented, but is less than the number of columns, then the system has infinite solutions with n minus the rank of A free parameters. So this matches sort of the last example we did in the computational video. It says that if the rank of A equals the rank of the augmented matrix, but those two ranks are smaller than the number of variables or the number of columns, then there will be solutions, but there will be infinite solutions. And we will need the number of variables minus the rank free parameters to actually solve the equation. All right, let's give a quick sketch of a justification for this guy as well. Okay, so once again, let's go ahead and put A into echelon form, row echelon form. So put A into row echelon form. Once again, we're just going to sort of make the assumption that we can get a leading 1 in the beginning. If there's a bunch of 0 columns at the front, it doesn't matter anyway. So we've got a 1 and then a sort of bunch of garbage. Then we've got 0, 1, bunch of garbage. Then that'll continue down into 0, 0. And eventually there'll be a new leading 1, and then there could be some garbage after that. And then there's some 0 rows down here. Okay, so now we're going to augment the matrix. But we know that the augmented matrix has the same rank. So when we do that augmentation, right, what we know happens is that there will be a bunch of values in here, but then once we get to these 0 rows, all the values down here must also be zeros. So these will all be zeros. We know that all these things down here must be zeros because if they weren't zeros, then the rank of A augmented would be larger than the rank of A because we'd have an extra non-zero row down here. Okay, so what does this tell us then? Well, This tells us, right, if we actually try to solve this system, well, we can try with that sort of back substitution again. But notice that a couple things happen that are a little different here. First of all, we avoid any sort of nonsense equations because all the 0 rows correspond to values of zeros here anyway. So we're safe in using this back substitution. But when we go to do this back substitution, right, notice that we have this many sort of constraints, right? We have rank of a constraints, but n different variables. How do we know that they have n variables? Because remember, the number of columns just always corresponds to the number of variables. So we've got rank of a constraints, but we've got n different variables. So if we solve that, we can get rank of a of the variables solved for. But the remaining variables will be sort of free choice. That means, this tells us, we can solve with n minus rank of a free parameters. In other words, if we let, right, n minus rank of a of those variables just be anything we like, a free parameter, then the other ones will be naturally solved through back substitution in terms of those free parameters. So, in other words, what we're saying is that the rank of a still tells us how many constraints we have, but since that won't match the number of variables, the remaining variables, n minus rank of a, must be able to be freely chosen using free parameters. All right, so that gives us our sort of last situation. Now we are ready to summarize all that into the sort of main theorem of this section. So let's go ahead and state this theorem. So we have this system ax equals b with a m by n. Now, again, just as sort of a note, m by n, of course, is the size of the matrix, but remember this can also be thought about as m equations, n variables. So when we say m by n, we mean we have m equations and n variables. Okay? So this theorem says if rank of a is less than rank of a augmented, this implies no solutions. If rank of a equals rank of a augmented, this implies solutions. How many solutions? Well, if rank of a equals n, then this implies unique solution, so just a single solution. Rank of a less than n implies infinite solutions with n minus rank of a free parameters. So there we go. There's sort of our main theorem in this whole section, which is to say that we can break it down into two cases with one case having a subcase. If the rank of A is less than the rank of the augmented matrix, we get no solutions. If the rank of A matches the augmented matrix, we know we have solutions. If that rank then is equivalent to the number of variables, the solution will be unique. If the rank is less than the number of variables, then we will have infinite solutions with n minus rank of A free parameters. Notice that this theorem tells you stuff that you guys have already sort of known, right? You'll know that a system of linear equations never has two solutions. It never has 10 solutions. It has either no solutions, one solution, or infinite solutions. That's something you guys learned way back in algebra, but now you've seen that proved through this theorem here. All right, let's briefly talk about how this theorem applies sort of specially to homogeneous systems. So remember, a homogeneous system is one where that b is equal to 0. So that means we have a system ax equals 0 with a m by n. Well, keep in mind that that sort of system will always have solution x equals 0. So this system will always have solution x equals 0, right? Obviously, you can just imagine that through sort of matrix multiplication. If you pop in x equals 0 here, and you do a times that 0, you know you're going to get that 0 there. So we'll always have that system, that have that solution x equals 0. Further, the system will have infinite solutions with n minus rank of a free parameters if rank of a is less than n. So the thing to sort of just note here, this means that for, let's not say for, that a homogeneous system is always consistent. Okay? So in a homogeneous system, you will never have this situation here where there are no solutions, because we know x equals 0 will always be a solution. So we know that there are solutions. If the rank of a equals n, then that will be the unique solution. And if not, then there will be infinite solutions with that form there. Note, this also tells you one other thing. Note, in homogeneous system, rank A equals rank A augmented, which should make sense, right? What are you doing in an augmented matrix? You're slapping on that extra column of values, but if that extra column of values is 0, that's obviously not going to change the rank. So we have those little extra notes there. All right, let's put all of this stuff together into sort of one example, trying to help you guys understand this sort of solution sense. Now, clearly, like from the previous video, you know that if you just have a system in front of you and you solve it, you will understand the solution set by just directly solving. What we're going to do in the next example is actually try to understand the solution set more based on information like the rank and the nature of the system. So it'll be a little bit stranger because we won't be able to just sort of rely on directly solving, but it'll help us understand this theorem. All right, so for this example, we've got some different sort of situations here, and what we're going to try to do is describe the solution set as thoroughly as possible. And if there are sort of multiple cases or things that can happen, we'll try to explain how those cases can arise. So in this first one, we've got ax equals b, and we're told that A is a 5 by 5 matrix. So in other words, we're dealing with a system that has 5 equations and 5 variables. And we're told that the rank of A is equal to 5. All right, so let's think about the options here. So let's think about A augmented first, right? So I'll solve these in a different color just so we can keep track of that. A augmented, in this case, will be, well, when you augment, you add that extra column, 5 by 6. So the first question we should ask ourselves is there the potential that the augmented matrix might have a higher rank than our original matrix? In other words, is it possible that the system will be inconsistent? So let's look at this matrix here. If it's 5 by 6, is it possible that it has a rank larger than 5? Well, no, because it only has 5 rows. And as we know, rank is limited by the number of rows and the number of columns. So this tells us, this implies that rank of A augmented must be 5. We know that because we know rank of A augmented has to be greater than or equal to the rank of A, and we know it can't be bigger than 5, and we know that it has to be at least 5, so we know that it is 5. So this tells us, right, there will be solutions. How do we know that? Well, that's because rank of A equals the rank of A augmented. Okay, well, if that's the case, what type of solutions are we looking at? Well, since the rank of A is 5 and the number of variables is 5, we know that that is equality there. So that means there will be a unique solution. So since rank of A equals n, this implies that this guy has a unique solution. So in other words, in this type of system, ax equals b, where A is 5 by 5 and the rank of A is 5, we know that that system is guaranteed to have a unique solution. Don't know what that solution is because we don't have any values, but we know it's going to be a unique solution. All right, let's take a look at B. B is ax equals 0, a is 4 by 3, and it has a rank of a is 2. So first thing we should sort of note here is this is homogeneous. So it has solutions. Well, how many solutions is it going to have? Is it going to be unique? Is it going to be infinite? Well, the n here is 3. The rank of a is 2. So this will have infinite solutions with 3 minus 2 equals 1 free parameter. How do we get that 3 minus 2? Well, that's the number of variables minus the rank. So we know that there will be 1 free parameter. All right, let's go ahead and try the next one, right? This guy's back to being ax equals b. A is 7 by 4, which means it has 7 equations and 4 variables. And the rank of a is 4 here. So this time we can't just assume that there will be solutions. So we need to think about a augmented. A augmented here will have an extra column. So it will be 7 by 5. So is it possible for the augmented matrix to have a rank larger than the original matrix? Well, the original matrix had rank 4. A augmented has to be at least 4, but it actually could be 5 because now we can see there are 7 rows and 5 columns. So we need to break this into 2 cases. If rank of a augmented is equal to 5, then that means there will be no solutions. Right? That is a possibility here, right? If the rank of a augmented is equal to 5, then there will be no solutions because the rank of a will be different than the rank of a augmented. Well, what happens if rank of a augmented is equal to 4? Well, that means there will be solutions because rank of a will match rank of a augmented. And since the number of variables was 4 and the rank of a and a augmented will be 4, that means that there will be a unique solution. So with this sort of setup, ax equals b, a is 7 by 4 and rank of a is 4, there is either no solutions or a unique solution. In other words, it is impossible for there to be infinite solutions. There is either going to be no solutions or a unique solution. All right, let's take a look at D. Ax equals b, a is 3 by 6, so 3 equations and 6 variables, and the rank of a is 3. All right, so a augmented will be a 3 by 7 matrix. So is it possible that this guy is going to have a larger rank? In other words, is it possible that its rank could be 4, right? Because we know the rank of a is 3. Well, since it's limited as 3 by 7, that's going to be impossible. So that tells us that rank of a augmented is also going to be 3. So since rank of a matches rank of a augmented, we know that there will be solutions. So we know that there will be, in this case, infinite solutions with, well, there were 6 variables and the rank of a is 3. So with 6 minus 3 equals 3 free parameters. There we go. So we know that in this sort of setup here, it is the only possibility is that there will be infinite solutions and we will need 3 free parameters to work through that. All right, next one here, we've got ax equals b. A is still 3 by 6, but now we're going to assume that the rank of a is 2. So let's go ahead and look at this. A augmented will be 3 by 7. Is it possible that the rank of a augmented will be larger than the rank of a? In other words, is it possible for rank of a augmented to be 3? Well, since it's 3 by 7 here, that is definitely a possibility. So if rank of a augmented is 3, then that will mean no solutions. If the rank of a augmented is 2, well, then the rank of a will match the rank of a augmented. And since there were 6 variables originally, that means there will be infinite solutions with 6 minus 2 equals 4 free parameters. So in a setup like this, where you have a 3 by 6 matrix that only has a rank of 2, that means either there are no solutions or you have an infinite set of solutions with 4 free variables. Finally, last one here, AX equals 0. That's going to be a homogeneous system, and it's 8 by 5 with a rank of 5 here. So what that tells us is this is homogeneous. So it has solutions for sure, right? So we don't even have to worry about A augmented or anything like that. We know it has solutions. So what type of solution set? Well, this will have, well, how many free parameters? It's got 5 variables, rank of 5. So this will have 5 minus 5 equals 0 free parameters. What does that mean? That means a unique solution. Actually, we can go a step further. This means the only solution will be x equals all zeros. Because we know that x equals 0, remember that's the vector 0, is always a solution to the homogeneous system. And we just showed that there's only a unique solution here, so it must be those all zeros. Now, I know that this is a pretty conceptual example here, but this is really just trying to help you guys understand the different possibilities with rank and how those sort of relate to the different solution sets as described by that sort of previous theorem. There's a couple examples of trying to do this sort of thinking on the suggested exercises, and I would recommend taking a look at those.